In this video, I'll be working through a series of exponential growth problems. Here's the first one. Cellular phone usage grew 22% each year from 1995 to 2003. Write a function to model the usage over that time period. So we're going to say y equals a b to the x. It's my exponential equation. We're going to start off with so many million, 34 million. So you can write 34, or you can write 34 million and just say that a is in millions. So we would write y is equal to 34. And then we're going to increase 22%. So if you're going up 22%, you're adding 22 pennies to the dollar. So one whole, and then you add 22 pennies more. So that's like 22% more. So this would be the equation for this. Now, this 34 means million, 34 million. So the output would be in millions as well. That represents the 22% change, and then the number of years. It's going to be the number of years past the starting point of 1995. So it'd be the number of years past 1995. So hardly anybody had cell phones back then, and it grew exponentially. This is kind of a weird graph. It's typically time would be here, but it's just to throw you off a little bit. Okay, the next problem is y equals a b to the x. We got to figure out if we're solving for a, b, x, or y. So it says a parent raises a child's allowance 20%. It starts off at 8 and it will end at 20. So we're going to start at 8. There's my starting point, 8, and we're going to end at 20. And it's 20%, so I'm adding 20 pennies to the dollar, so it's 1.2. So if b equals 1, there's no change, right? B equals 1 is no change at all. But when you add numbers, add percents, add pennies onto the dollar, to pretend like that's a dollar, you've just made it 20 pennies or 20% more than the dollar, so that's an increase of 20%. Okay, we're going to divide. By 8, we get 2.5 is equal to 1.2 to the x power. I dropped the 0 out. We have to bring the x down. In order to bring the x down, I take the log of each side of the equation. That brings the x down to the front. That's the property that we've talked about. So it is log 2.5 is equal to x log of 1.2, or 1.20. There's multiplication there, so we're going to divide back the log. So those cancel out. X is now by itself. That's the exact answer. You type this into the calculator, and you get x is approximately equal to 5.026 years. Okay, problem number 9 is a two-step problem, so I'm going to draw a line here to make it in 2 steps. We have to figure out how many how long it's going to take for 10,000 manatee to appear in Florida. So we have a starting amount of 1465 in 1991 and a stopping amount of 3276 in 2001, and we want to know how long it takes to get to 10,000 manatee. I'm going to use y equals a b to the x for my exponential model. So I'm starting off with 1465 manatee. I don't know the growth rate, so that's b, but it's a 10-year period of time, so it's to the 10th power. And my stopping amount is 3276. There's multiplication right there, so I'm going to divide over the 1465. And I'm going to leave that fraction because that fraction is they're going to make a really awful decimal, so I'm just going to leave that. The opposite of the 10th power is the 10th root, so it's the 1/10th power. So what I have to type into the calculator is 3276 divided by 1465 to the 1/10th power, and that would be equal to b, which is approximately equal to, so I'm typing this in. Here, I'll type one in just to make sure we're all kosher here. 3276 divided by 1465 to the power of 1 divided by 10, 1/10. Or I actually could do 0.1, which is also the decimal approximation of 1/10, or the exact decimal. So I'm rounding to 4 decimal places because that 0 right there makes me think, hey, I'll just keep 4 decimal places. So it's 1.0838. Now we have to go ahead and come up with how long it takes to get to 10,000. So we're going to start off with the equation y equals ab to the x again. My starting point, I could pick either starting point, but I'm going to pick 3276. I know b is 1.0838. Now, if you kept this answer in there, it'd be exact, or as exact as possible. Now I'm looking for how long, so I don't know x. My stopping point is when does it hit 10,000 manatee? Past 2001. Okay, so I'm going to divide over the 3276 because there's multiplication there. And that leaves me an awful fraction. And then I have 10,000, 3276 is equal to 1.0838 to the x power. And I'm going to take the log of each side, right, because that brings the x down to the front. So x is now down here in the front. That's not there. So I'm going to then divide over log 1.0838. 838. So this cancels out. The x went to the front. The logs cancel out. See, x is by itself because those are gone. That went to the front. We type all this in, and we get x is approximately 13.86 years. And that's 13.86 years past 2001. So it's like sometime in 2014, 2015 when this happens. And I think the manatee population is pretty close to 10,000 now. You'd have to look it up on the internet, but I think it's definitely improved since these conservation efforts have worked. Number 10. They give you the model right here. Y is equal to 281,001.0124 to the x power. This is the U.S. population model. So it's only growing 1% and then a little bit more than the 1%. So it's 1.24%. That's how you would read that. So it's growing kind of slow, but 1% more, 1% more, it's still growing at a pretty good rate here. And this problem came from an older math book, so who knows. The question is, when will it hit 350 million? So we're going to change this y here into 350. So the 281 represents million, and we're changing it to 350 million. So you could put all those zeros there, but when you divide it over, the zeros would all cancel out. So here we go. We're going to solve this like we did up here. We're going to divide, take the log, bring the x to the front. So 281 on each side. This cancels out. And again, that's an awful fraction, so I'm going to leave it. So I have 350 over 281 is equal to 1.0128 to the x power. Take the log of each side, right? Why do we take the log? To bring the exponent to the front. So that's not there anymore. And then I just divide the log back over. 24 log 1.0124, and I type this into the calculator. It almost looks identical to the last one. So it's log of this fraction divided by log of this number. So you type it in, and I'll type one in here just to make sure we're on the right track here. I'll type this one in because I'll maybe do every other one or something like that. So it's log 350 divided by 281. So it's 350 million divided by 281 million, close the parentheses, divided by log of the growth rate, 1.0124. All right, enter. So 17.82 or 818. So x is approximately equal to 17.8188 years. And that's past the year, year 2000. So that means 2000. That means like right now we should be, because it is 2017 and almost 2018. So it means we should be close to 350 million. I'd have to look up what the population is right now. We could Google that. Let me Google it real quick. So I looked it up here. Siri tells me that the population is 325 million, and that's what it's saying. And then this model here from the year 2000 was saying that right now we should be to 350 million. So the model is adjusted. It didn't grow as quite as fast as what was predicted. So this is the year 2000. This probably came from a math book that was written in the early 2000s. Okay, this is a true story about my mom, Mrs. Jackie, and she is a lovely lady, my mom, and this is a true story about what happened to her. My parents moved to town in 1990, and they bought a house for $86,000. So we have y is equal to ab to the x, and my starting amount is $86,000, and my final amount that the house was sold for was $134,000. And we don't know the growth rate because that's what's saying what was the growth rate during that time period, and we know that it happened over a 15-year period of time from 1990 to 2005. So this actually was the national average right at this moment. Was that her house grew during that time period at a certain percent per year, and it followed it like perfect right at the national average. So we're going to solve for b, so we had to undo the power this time. So we're going to do the 15th root in a second. So divide by 86,000. When you divide, those zeros all cancel out because it'd be like dividing each one of them by 10, by 100, by 1,000, so you're left with that. You could even divide each of those by 2, but since I'm using a calculator, I'll just leave it. 134.86 is equal to b to the 15th power. So we're about to see my mom's growth rate here in a second. Of course, my mom isn't growing anymore. Her growth rate's over as a human. Actually, she's a little bit older, so actually she's shrinking, maybe. So the 15th power, the 15th root, those would cancel out. So you get b is approximately equal to this. So we type that in the calculator, and it's really close to 1.03. So what does 1.03 mean? It means that it's 3% more per year. So it's 3% more. So that was the growth rate, 3% more each year. And that was the national average during that time. And then shortly after that, there was the whole real estate bust, and people couldn't make their payments and all that. And that was about, what, 2008, 2009. So she sold her house at the right time. Of course, it's not pure profit, right? She didn't go, oh, I have 86 and now I have this. She didn't profit that amount of money because she did things to improve the house during the time, a roof, some windows, some siding, things like that. But she still made a sizable amount of money off of that real estate investment. Okay. The next one is really straightforward. We got y is equal to b to the x, and it says we have a stock price of $40 and we're going to change it to $50. So my final amount's 50, my starting amount's 40, and it's growing 8% a year. So we're adding 8 pennies to the dollar. Adding 8 pennies to the dollar would be 1.08. So this one solves out like the ones where you got to do the log business to bring the x down to the front. So I'm going to divide over the 40. Now, dividing 40 into 50 works out really nice. It's 1.25 and 1.08 to the x power. So it makes it look a little bit nicer. When that fraction is nice, it really makes a good decimal and all that. So terminating decimals with 2 decimal places are pretty nice decimals, aren't they? Log of each side, and that brings the x down to the front. So I get log 1.25 is equal to x log 1.08. There's multiplication right there. It's x times this. So I undo the multiplication by dividing each side by log 1.08. So that's the answer for x exactly. So x is approximately equal to that answer. So I divide that on the calculator in about 2.9 years. 2 left. This one is about doubling a penny. This is a famous problem. If you double a penny, and then you think if you just double a penny a bunch of days and keep doubling the amount, it'd be like, well, it'd take forever to get to large numbers, but it actually grows really fast. It grows exponentially. So we start off, we're comparing a $20,000 car versus doubling a penny. That's what this one says. So we say y is equal to a, b to the x. We have, starting off with a penny in dollars. We're doubling, so that means we're going to multiply by 2 because we're 100% more. So it's twice as much, right? That's what doubling means. So we're adding 100 pennies to a penny, to a dollar, 100 pennies to the dollar to make it like 2. So it's doubling. And we're going to go to 20,000. So same thing, divide over. And that would be 2 million, moving the decimal point, is equal to 2 to the x. So how we solve this is an exponential equation because the variable's in the exponent spot. So we're going to divide, not divide, we're going to take the log of each side, which brings the x down to the front. And so we get x log 2. There's multiplication in between there, so we divide the log 2 over. That cancels out, log 2. So the answer is log 2 million divided by log 2. And that would be, type that in the calculator, x is approximately equal to, and I'll type a few into the calculator. So we get log of 2 million divided by log 2. So 20 it's days, how many days? So 20.9 days, so basically 21 days. Okay, the last problem is a population of a city. So P is equal to P initial 1.12 to the T. No, it's not a population of a city. It's a population. I automatically said it's bacteria. So 0.12 means it's growing 12%, right? 12 pennies added to the dollar. So we want to go from, it starts with 200, and how long to get 1,000. So we start off with 200, and we go to 1,000. All right. So I do the same thing I've been doing here. There's multiplication here. So that means I'm going to divide this over. Now again, that divides really nicely. That's just 5. So 5 is equal to 1.12 to the t power. Do the log. Do the log. Bring the t down to the front. So it's going to be log 5 is equal to t log 1.12. There's multiplication in between here, right? So that means I have to divide it over. We always do the opposite when we solve equations. That cancels out. That's the answer, the exact answer. So t is approximately equal to, type it in the calculator, 14.2 minutes. So that keeps changing. When it's x, it could be the number of years, right? This will be minutes. That exponent changes every time, what the units are. So this was the number of minutes. This was the number of days. This was the number of years. Here we were looking for b, so we didn't solve for the exponent. Number of years, number of years. Here we solved again for the exponent, number of years. Okay, so it's representing something that's how many times it changes. So that's our growth model here. And this one is for a specific one. Your starting point, your stopping point, your change, and then how many times it changes. Well, this changes for 14 minutes. Okay, so it's 1 minute change, 2 minutes changes. It changes every minute. So that's that because it's how the bacteria are changing. So the bacteria are changing pretty quickly. Went from 200 to 2,000. That's a heck of a lot of bacteria. Bacteria, yuck. All right. So refrigerate your food. That'll keep the bacteria, temperature helps control the amount of bacteria. So refrigerate your stuff.